What's up guys, welcome back to a new video. In this session we're looking at how to use surface integrals, also known as double integrals, to calculate the surface of arbitrary two-dimensional figures. And this video actually serves as an introductory video on my video on volume integrals, because many concepts are much more easy to understand in 2 dimensions before going to 3 dimensions. In particular, we'll be using surface integrals in both Cartesian and polar coordinates, because there's a crucial difference between them. As always, I will explain every step along the way, and in this video there will be a mix of theory and exercises. If you have any questions or suggestions, leave a comment down below. And with that out of the way, let's get into it. In the first exercise, we want to calculate the surface of a standard rectangle with sides A and B. Of course, we know what the surface of a rectangle with these sides is, but now we want to do it using surface integrals. And before we do anything else, we draw ourselves a coordinate system. And in this case, what suits us best is a Cartesian coordinate system. So we have an x-axis and a y-axis. Now to calculate this surface using surface integrals, we need of course to remind ourselves what an integral actually is. In 1 dimension, we know that the entirety of the x-axis is calculated by the integral over dx, and dx is the infinitesimal length in the x direction, from minus infinity to plus infinity. And the same goes for the y-axis. If we want to encapsulate the entire y-axis, we also integrate from minus to plus infinity, but this time over an infinitesimal length in the y direction. However, these integrals are both in 1 dimension. And since we're dealing here with a surface, we need to think about integrals in 2 dimensions. And in a similar fashion that we had an infinitesimal length in the x direction and an infinitesimal length in the y direction, to look for surface integrals, we need to think about what the infinitesimal surface is. Because if we can integrate this surface over the entire plane, then we know that we will have our total surface of the entire 2-dimensional space. So what is the infinitesimal surface element? Well, let's first draw it out of proportion in our figure right here. Let's say that this is indeed the infinitesimal surface element dA. So what is its surface? Well, we know that in the x direction, this will be the infinitesimal element in the x direction. And in the y direction, this will be the infinitesimal length in the y direction. So we see that we have a square here, dA, which is made up of lengths dx and dy. This gives us the information that the surface of dA is simply equal to the length dx multiplied with the length dy, because that's the surface of a square with length dx and dy. Now, if we want to integrate this, of course, we now have 2 integrals, the integral over dx and the integral over dy. And because we're integrating over the entire plane here, we know that we have to integrate from minus infinity to plus infinity for x, and also for y we have to multiply from minus to plus infinity. And this is how we have rewritten this 2-dimensional integral, this surface integral, as the product of 2 1-dimensional integrals. What this basically means is that if we want to have the entire surface of the plane, then we simply integrate x from minus infinity to plus infinity, but now for every value of y. So at this point, we already have an expression to get the total surface of the plane. Namely, we integrate x from minus to plus infinity, and we multiply this with the integral of y from minus to plus infinity. However, we don't need to integrate from minus to plus infinity to get the surface of this rectangle that we are looking at. Because for x we see that we are integrating from x is 0 to x is equal to a, and for y we are also integrating from y equals to 0 to y equals to b. And basically these numbers are the boundaries of these 1-dimensional integrals that we use to rewrite our surface integral. So let's see how this goes. We get the integral over dx from 0 to a. And of course, we then have also the integral over dy from 0 to b. And what this basically means, that we're integrating in the x direction from 0 to a, and we do this for every value of y from 0 all the way up to b. And this is how we will obtain the surface of our rectangle. So let's now simply calculate these integrals. So the integral from 0 to a over dx is simply x filled in the boundaries, so 0 and a, and we multiply this with the integral of y from 0 to b, which is simply y filled in the boundaries 0 and b. And this simply becomes a minus 0 multiplied by b minus 0, which is of course a times b. And this is the surface of this rectangle that we had. And of course we already knew the surface of this rectangle, because the surface of a rectangle is simply the multiplication of the length of its two sides. However, now we obtained this result by using a surface integral. And in the same systematic way, we can now also calculate other surfaces. So let's look at the following figure. Let's say we want to calculate the surface of a square with side r. Now, of course, we already know that the area of this square will be r squared. However, let's do this with the method that we learned using surface integrals. And let's make it a bit more difficult so we get more practice and more understanding of what we're really doing. Let's say that we're now drawing our coordinate systems like this. So we have the x-axis here and the y-axis there. And let's say that the x component of this corner is a and its y component is b. Now we trivially know that the x component of this corner will be a plus r, because this distance is r. And likewise, of course, for this corner, we have a y component of b plus r, because this distance is also r. And at this point, we will use what we have learned to calculate this surface of this square. We know that the surface of this square will be equal to the integral of dA over this square. However, what is dA? Well, we figured out that dA is simply the product of dx times dy, because we're still working in Cartesian coordinates, where we know that the infinitesimal surface element dA is simply the product of dx and dy. And of course, we need to integrate both of these infinitesimal one-dimensional elements. And it's the boundaries of these two integrals that will determine the surface of our square. For dx, we see that we are integrating from a all the way to a plus r. So we just write it down here. We integrate from a to a plus r. In the same sense, we are integrating y from b all the way to b plus r. So we integrate from b to b plus r. And now we have two integrals that we can very easily integrate. We have that this is equal to x filled in the boundaries. The boundaries are a and a plus r. And we multiply this with y also filled in its boundaries, which are b and b plus r. This, of course, is simply equal to a plus r minus a multiplied by b plus r minus b. And we see that these a and b very conveniently drop out. And we are, of course, left with r times r, which is equal to r squared, which is the surface of a square. Now, these a's and b's dropping out clearly shows that it didn't matter that we put our square not in the origin of our coordinate system. These coordinates a and b will always drop out. Before we go to polar coordinates, let's first consider a more difficult exercise in Cartesian coordinates. Let's say that we want to calculate the surface of the following triangle. This side has a length a and this side has a length h. And as I said, we are going to do this in Cartesian coordinates, so we draw our axes x and y. Now we want to calculate the surface of this triangle. And there's actually two ways of using surface integrals to calculate this surface. One way, which we will do first, a bit more complex but more general, so you can apply this method to more complex figures. And then there's one way which is quick and easy, but will not apply to more general figures. And we will do this one afterwards to check whether our result actually is correct. The first step in Cartesian coordinates, as always, is to write our infinitesimal surface element as being the product of the x, so the infinitesimal element in the x direction, and the y, the infinitesimal element in the y direction. And therefore we know that the surface of the entire plane is equal to the integral over our infinitesimal surface element, which is of course equal to the product of the integrals of dx and dy. And as before, if we are looking at the entire surface of the plane, we have to integrate x and y from minus infinity to plus infinity. If we now want to translate this to the surface of our triangle, then we know that the only thing that needs to change are the boundaries of these integrals dx and dy. And whereas in previous exercises this was very clear what these boundaries were, we see here that we have kind of a problem. Let's say for the integral in the x direction that we indeed integrate from 0 to a. However, we see that if we want to integrate then in the y direction, that for x is equal to 0, we indeed integrate from 0 to h. However, with every increasing x, the boundary of our y integral will change. It will decrease, as you can see here. And if x is equal to a in this point, we see that we don't have to integrate over y at all, because there is no distance. This means that if we do integrate from 0 to a in the x direction, meaning from here to here, that our boundaries in the y direction will actually change. They will always go from 0, so along this line they will always start from 0. However, we see that their endpoint, their upper boundary, will decrease as x increases. This means that our upper boundary of y will depend on x. And this is why I denote this upper boundary here as y as a function of x. And because this integral, its upper boundary, is dependent on x, this is not simply a product of two integrals anymore. Let's now see what this becomes. We cannot simply calculate this first integral because we see that this upper boundary of the second integral depends on x. So we cannot at this point calculate this first integral, so we simply copy it and write it down. Then the second integral we can calculate because there's only one thing that depends on y, and this integral does not depend on y. So we simply calculate this, which then becomes y filled in its boundaries 0 and y of x. And again, this y of x is simply this value along this steep curve of the triangle, which decreases as x increases. So this simply becomes the integral from 0 to a of this function now, which also depends on x. So we can put dx right here, and we see that we have here y of x, the upper boundary, y of x, minus 0, minus 0. And this will be now our integral. And of course we can drop this minus 0 because it doesn't really matter. And we are left with this integral. So we're integrating over x from 0 to a of a function y that depends on x. And what is this function? It is simply this slope side of our triangle. That would be our function y of x. So now it means that we have to figure out what this y of x is as a function of x. And we see that this y of x is a simple linear curve. So we know that y is equal to minus the slope of this curve times x. And the slope are two numbers that we will figure out in a moment. And we add to this h, because we know that if x is 0, meaning at this point, then y will be indeed h, the height of the triangle. So at this point, we still need to figure out the slope of our linear curve. And the slope simply comes from the following reasoning. If we go a in the x direction, then we descend h in the y direction. This means that this fraction becomes h over a, because if x is equal to a, then these two cancel out and we have minus h plus h, which is 0. So at x is equal to a, which is here, we indeed have that y of x is equal to 0. And this will be our function which is just the linear function of the slope of our triangle. This means that we now have y, which we can fill in our integral, which we can then integrate over x. And let's see what this becomes. So we get that the surface of our triangle is simply equal to the integral from 0 to a of minus h over a times x plus h dx. And this is now a very simple function that we can integrate. We know that this term simply becomes h multiplied with the integral of 0 to a of dx. And we know that this first term has an x inside of it, so this will simply become minus h over a, because that's just a constant which can be put outside of the integral, times the integral of 0 to a of x dx. And now, of course, we can take this home. So we have this integral being equal to h multiplied by a minus 0, simply the upper bound minus the lower boundary, minus h over a multiplied with the following, and the integral of x dx is 1/2 times x squared, and we fill this in the boundaries 0 and a. We can calculate this to be h times a minus h divided by a multiplied by 1/2 times a squared, because this 0 simply drops out. This, of course, is equal to cancelling 1 power of a right here. We have h times a minus 1/2 times h times a. And this, of course, gets us our final result, which is 1/2 times h times a. And we see that this is indeed the surface of our original triangle, because our triangle had as a base length a and as its height length h. And we know then from basic geometry that indeed the surface is equal to h times a divided by 2, which is of course equal, so we didn't make any mistakes. And this is a roundabout way how we used surface integrals to calculate the surface of this triangle. And as I said, there's also a second way of solving this problem. Let's draw again our triangle of our original problem. Draw on it the x and the y coordinate axis. And now again, we need to calculate this surface. And in this fast way of solving it, we just see that the surface of this triangle is exactly half the surface of this rectangle. Because we see that the surface of this rectangle is this surface, and the surface of the triangle is of course this surface, and it's exactly half. But we know already how to calculate the surface of a triangle. That's exactly the first exercise that we did. So we simply calculate this right away. We know that for x, we calculate from 0 to a. So we calculate from 0 to a. And for y, we calculate again from 0 to h. So these boundaries become 0 to h. And this can be very easily calculated as being a minus 0 multiplied by h minus 0. And this is of course a times h. Now we know that the surface of the triangle is equal to 1/2 the surface of the rectangle. So we know that this is 1/2 times a times h, and this is again the same result as we had before, but now obtained much more easily. However, this is of course not applicable to more complicated figures, whereas the previous first method was exactly more applicable to other figures. Let's now go to an exercise on polar coordinates where we want to calculate the area of a circle. Let's say this is the circle of which we want to calculate the area of, and we know that the radius of this circle is simply r. Let's say that you really want to calculate this surface using Cartesian coordinates. So let's see in what kind of problems you would run into. And for Cartesian coordinates, we know that the infinitesimal surface element is simply equal to the infinitesimal element in the x direction and the infinitesimal element in the y direction. So simply a infinitesimal square. And of course, then we know that the surface of our figure that we want to calculate is equal to the integral over this infinitesimal surface element, which is of course equal to the integral over these one-dimensional x and y infinitesimal elements, and it is determined by the boundaries. However, in this case, we see that the boundaries are very hard to determine in this case, because if we integrate over x, we see that the boundaries over which we integrate x decreases when y increases. And likewise, if we want to integrate over y, we see that these boundaries also change by changing the x. It's basically the same as we did for the exercise on the triangle. However, because this is a circle, it's much less evident to find these boundaries. So what we can do instead is to look at polar coordinates, which are denoted as r and an angle. Let's see how this looks in case of our circle. The r coordinate is simply the distance from the origin of our point. This is the r axis. And then the angle coordinate is simply the angle that our point makes with the r axis. In this case, the axis is horizontal. Since for our circle, the r component will always be capital R, because that's the definition of a circle, this point right here, for example, is denoted by capital R and an angle phi. And it is these two pieces of information that completely determine the location of this point. And whereas in Cartesian coordinates, the function of a circle is quite complex and very difficult to integrate, the function here is simply that the r component needs always to be equal to capital R, the radius of the circle. And this is a much easier function to deal with. So at this point, we already know that we are going to be using polar coordinates. However, this raises the question, what exactly is the infinitesimal surface element in polar coordinates? Let us just simply recap. In Cartesian coordinates, so in an x and a y axis, we have x and y, we could divide our plane into infinitesimal squares, and the surface of each of these squares was then the infinitesimal element dA in Cartesian coordinates. Let's, for example, take this one. Here we see that this infinitesimal element was simply dy multiplied by dx. And moreover, we see that this will always be dy multiplied by dx wherever in the plane we are. This will always be exactly the same surface, dA being equal to dx multiplied by dy. However, some of you might already see the problem, because if we divide the plane not in equal squares of dx and dy, but instead of polar coordinates, we will get the following. So let me first draw the same plane, but now divided by polar coordinates. In this case, we see that the first infinitesimal element is the infinitesimal length in the r direction, so a radial direction. And the infinitesimal element in the angle direction will be this one. And thus we see that the infinitesimal surface in polar coordinates will be this surface. So this is the surface that we need to calculate. It's basically bounded by two infinitesimal elements in the angle direction and two infinitesimal elements in the radial direction. So let's see how we calculate this surface. So we have that dA is equal to, and let me now sketch the surface that we need to calculate. So it will be something along the lines of this, with here dr and here d phi. And because we know that dr is so small, we can neglect the difference between these two distances. Because if dr is very small, then these two distances will be approximately equal. So we have to calculate this surface right here. And whereas in Cartesian coordinates, we simply had dx times dy, we here absolutely do not have that. This is simply dr multiplied by d phi. And why this is because these sides of our surface are curved. And we know from basic geometry that if we want to get the length of these two curved sides, that we have to multiply this d phi, so the change in angle, with r, the absolute value away from the origin. And if we do this multiplication with r, then this is indeed the infinitesimal surface element. And having an expression for the infinitesimal surface element, we can now directly calculate the surface of our circle. We know that the surface of our circle is simply equal to the integral of our infinitesimal surface element. And because we are working in polar coordinates, we know that this is simply equal to the double integral of this term right here. So we have r dr d phi. And now, of course, as was the case in Cartesian coordinates, it's these boundaries of these two integrals that we indeed need to determine in order to get the surface of our circle. So let's again draw our circle right here. Let's draw the r-axis and the phi axis right here. For the integral over dr, we know that we have to integrate from r is equal to 0 all the way up to r is equal to capital R, the radius of our circle. So for the r integral, we integrate from 0 to capital R. Now for the other integral, so the phi integral over the entire angle, we know that we have to integrate over the entirety of this circle, all the way around. So this means that we integrate from 0, the angle being 0, all the way to the angle being 2 pi, meaning right here. So all the way around. And at this point, we have our integrals that we want to calculate. We have the integral from 0 to capital R of r dr, and we have the integral of 0 to 2 pi of d phi. And this we can very easily calculate because we get 1/2 times r squared filled in the boundaries, multiplied by phi filled in the two boundaries. And this is simply equal to 1/2 times r squared multiplied by 2 pi. And this, of course, gets us, by canceling this 2, that this is equal to pi times r squared. And this is indeed the surface of a circle with radius r. And this brings us to the end of this video, and I hoped that you learned something more about how to use surface integrals. If you learned something, give this video a thumbs up, and if you want to get notified by future releases, consider subscribing. And with that, I thank you for watching, and I will see you guys in the next one. Bye.